Hello, good morning. Myself, Dr. Shaila Dinkarapte. This is the second video in the series of digital signal processing. The topic for this video is properties of DFT. So let's begin with that. Firstly, we'll see how DFT can be used as a linear transformation. So it is represented as, you can say, a matrix multiplication. So this is the formula for discrete Fourier transform. We have seen that discrete Fourier transform is a discrete version of discrete time Fourier transform. So discrete time Fourier transform is a continuous spectrum, and we take one period of it and sample it at regular intervals using capital N number of samples. So there will be capital N number of DFT coefficients. So this K will be running from 0 to capital N. And we represent a formula for DFT in this manner, and this is the formula for inverse DFT. Here there is a term called as e raised to minus j 2 pi k n upon capital N. Instead of writing this every time, normally what we do is we represent e raised to minus j 2 pi by capital N as W. Then this just becomes W raised to kn, right? Now this W, this particular matrix, suppose it is n by n matrix, then it will be represented like this. The corresponding matrix, that is for the first row and the first column, it will have the value equal to 1, because when k or n is equal to 0, e raised to j0 is equal to 1. So the first row and the first column will be equal to 1. Now using this linear transformation or using this matrix, how to calculate the Fourier transform? Now in this case, you will remember that e raised to j omega t is nothing but cos omega t plus j sin omega t. That means the corresponding basis functions used here in Fourier transform are sines and cosines, because they are perpendicular or orthogonal to each other. We are using orthogonal basis functions. Now let us consider a 4-point matrix, W matrix. We will have to write the value of k and n respectively from 0 to n minus 1, that is 0 to 3, and if we evaluate, we get this corresponding matrix. So W4 raised to 1 means e raised to minus j 2 pi by capital N into nk, where n is equal to 1 and k is also equal to 1. So what the value will be, it is equal to minus j. So that is how you have to calculate, and you will get this matrix. So if this is the value of W, this is the matrix W, and if the signal is having the 4 samples 0, 1, 2, 3, then we have to do the matrix multiplication and get this particular output as the DFT. Now if you look at this DFT, you will find that this x0 is real, x of n by 2 is real, in this case it is 4, so x2 is real, and other two values, they are complex conjugates of each other. Now if you want to calculate inverse DFT, naturally what you will have to do, you will have to use the transpose. Star means it is the complex conjugate of this particular matrix. So rows will be changed to columns and columns will be changed to rows, and then you multiply it by the corresponding DFT coefficients we have calculated. The matrix multiplication will result in the samples 0, 1, 2, 3 as the recovered signal, which we have used as a signal at the start. Now let us see what are the properties of this DFT. There is a property called as property of periodicity. We have linearity property, complex conjugate property, time reversal property, circular time shifting property, circular frequency shifting property, and property of multiplication of two DFTs, namely the circular convolution. So let us see one by one all these properties. Periodicity property. So what is periodicity property? If xn and xk are n-point DFT pair means xn transforms to x of k. Xk represents the DFT values and xn represents the signal values. then in that case x of n plus n is equal to xn for all n. That means after every capital N samples, it will repeat. X of k plus n will be equal to x of k for all k. Why this is so? Because if you calculate x of capital X of k plus n, means here I will have to substitute k plus n in the formula. Now when n k plus n by n, if I just split, it will be k divided by n as the first term, and in the second term I will just have e raised to j 2 pi and k a raised to j 2 pi n is equal to 1, e raised to minus j 2 pi. If it is multiple of 2 pi, it will be equal to 1. So because this is equal to 1, this term will go away and it will be same as x of k. So periodicity property is easily proved. Property of linearity. What is linearity? As we have already seen, we are using only discrete systems, those are linear. So we are using LTI systems, linear time invariant systems normally. So the linearity property will hold good for all types of transforms. In this case, if f1 x1n transforms to x1k and x2n transforms to x2k, then a1 into x1n plus a2 into x2n transforms to a1 into x1k plus a2 into x2k. This is what is called as the linear combination. So superposition holds good here because the system is linear. Then we have the complex conjugate property. If xn transforms to xk, then x of n by 2 minus k is same as x of n by 2 plus k. So this is the complex conjugate property. You will see that x of 0 and x of n by 2 will be real, and the corresponding other DFT coefficients will be complex conjugates of each other. We will see this later. So in order to prove this, we are calculating x of k. This is the formula for x of k. Now what will be x star of n by 2 minus k? Here star is representing the complex conjugate because the corresponding DFT coefficient is complex. So x star of n by 2 minus k, you write it as x of n varying from 0 to n minus 1 xn wn star n by 2 minus k. Now this w star of n by 2 minus k, I can also write it as wn n minus n by 2 plus k. So it is equal to n is equal to 0 to n minus 1 wn raised to n by 2 plus k plus wn raised to n means star complex conjugate. This is equal to 1 because that in that case n will cancel and you will have e raised to minus j 2 pi n, which is equal to 1 as we have seen. And we can also see that if this is so, wn minus n by 2 plus k is same as wn n by 2 plus k, because this is a complex conjugate. You can easily verify this but by just directly writing down the formula. So suppose we consider 8-point DFT. Then as I said, x0 and x4 will be real. X1 will be complex conjugate of x7, x2 will be complex conjugate of x6, x3 will be complex conjugate of x5. This is what is called as complex conjugate property. Now x2 and x of n by 2, x0 and x of n by 2 are real if the sequence xn is real. That is important. If the signal itself is complex, then the corresponding DFT coefficients will not show any complex conjugate property. So x0 is equal to summation n varying from 0 to n minus 1 x of n wn raised to 0, because this we are calculating zeroth coefficient. So x of n xn into wn raised to 0 is what? Wn is e raised to minus j 2 pi by capital N. Now if k is equal to k and n are 0, then this will be equal to e raised to minus 0, that means it equal to 1. So it is equal to xn. So this is real. If xn is real, this will be real. Then x of n by 2 will also be similarly evaluated. This will be x of wn raised to n by 2. So it will be minus 1 raised to n. So again it is real. DFT illustration. Let us consider the signal xn as 1, 2, 3, 4, 5, 2, 3, 1. These are the samples taken for illustration. Then we can calculate the DFT using MATLAB. So this is these are the DFT coefficients, those are found. You will find that x0 is real, then x4 is also real. This is complex conjugate of this is complex conjugate of this, and this is complex conjugate of this, as already illustrated. Now this is the magnitude plot of a DFT of the sequence. Now in this case you will see that the magnitude values are symmetrically same, and only this x0 value will be the DC component, and x of center value, x of n by 2, will also be real. Then we come to time reversal property. What is time reversal? If it is x of n, I write it as x of minus n. That is the time reversal property. But we are considering that to the base n, this indicates that this is periodic with period of capital N. So in that case, how this x of minus n can be written as x of minus n can be written as x of n minus n. So how it will transform to? It will transform to x of minus k. That means it will transform to x of n minus k. Right. So x of n minus n transform to x of n minus n. That means it will transform to x of minus n. So this is same as x of minus n. That is why x of minus n transforms to capital X of minus n. So we'll see how this happens. So process of time reverse, how time reversal occurs. So let us say these are the sample values 1, 2, 3, 4, 5, 6, 7, 8. These are the sample values, those are considered. Now original sequence is x0, x1, x2, etc. up to x7. Now how the time reverse sequence will occur? What is time reverse sequence? X0 will be kept as it is. X7 will take the value of x1. X6 will come here, then x5, then x4, then x3, then x2, and then x1. This is how the time reversal takes place. So original sequence is x0, x1, x2, x3, x4, x5, x6, and x7. The time reverse sequence x0 will be kept as it is. X1 will be replaced by X7, X2 will be replaced by X6, and so on. So it is just reverting in time, That is time reversal. So if it is time reverse, sequence is time reverse, what will happen to the DFT coefficients? The DFT coefficient magnitude will remain the same. What will happen to the phase? The phase will be reversed. So if here the phase is 0, it will remain the same. Here the phase was minus 80, it will become plus 180. This is plus 180, now it will become minus 180. Whatever phase is there, no, it will get reversed. The phase will reverse in this case. Here also the phase reverses. So the phase change of 180 degrees for each sample will occur, and the magnitude response will remain the same. So if I time reverse the sequence, what happens to the Fourier domain is we get a phase change of 180 degrees for every sample. Property of circular time shifting. Now suppose we circularly time shift the sequence. So if we have the signal xn, sequence xn, and now if we generate the sequence zn, the discrete time signal is also called as a sequence. So Zn is a shifted sequence with respect to Xn. So how Zn is written as? Zn is x of n minus h, where h is the amount of shift, and it is it is having the periodicity. So capital N is represented as a period over here. Here a double parenthesis is used to indicate that x of h minus n minus h is capital N periodic, and h is the amount of shift, as I said. So what will be happening to x of k? That is the Fourier discrete Fourier transform. So it will be what will happen is it will multiply by w raised to kh into x of k. So whatever is the x of k, it will be multiplied by w raised to kh this w raised to kh will have magnitude value equal to 1. So magnitude response is unaffected. Only thing is the phase response will change by wn raised to n into k. Now how this phase response changes, let us see. Magnitude plot is unchanged as we have seen. Consider time shift of two samples. Suppose we shift the signal by two samples. The phase change will occur. How the phase change will be? The phase change of pi by 2 into k. So if I am using two samples time shift, then there will be a phase change of pi by 2 into 2. So there will be a phase change of pi occurs for every kth sample. So if I consider, say, see this is the DFT of xn. Now I want to plot the angle for every particular sample in the shifted sequence. So suppose I am having the sample time shift of two samples. Then how the phase change will be? Phase change will be pi k by 2. Why this 2? This 2 is because there is a time shift of two samples. Now what is k? K is the corresponding sample number, right? So if k is equal to 0, k is equal to 0, no phase shift occurring, right? Now if k is equal to 1, there will be a phase shift of pi by 2. If k is equal to 2, there is a phase shift of pi. If k is equal to 3, it will be equal to 3 pi by 2 and so on. So for every sample, phase value goes on increasing by pi by 2. Property of circular frequency shifting. So suppose instead of shifting the time sequence, if we shift the DFT, if we shift the DFT by h samples, this is n periodic. So again it is represented by double parenthesis and capital N is written, indicating that it is capital N periodic. Now, what will happen to the time domain sequence? The time domain sequence will be multiplied by Wn raised to minus nh. So there will be a phase shift in the time sequence. Now, because if there is a phase shift, the corresponding input signal will not remain real, it will be complex. And when xn is not real, the corresponding DFT will not show any complex conjugate property. Here double parenthesis is used to indicate that x of k minus h is n periodic. Now what will happen? See, this is giving the proof. What is x of k minus h to the base n? It will be equal to xn w raised to minus nh, because h is the amount of shift, wn raised to nk. So this is k minus h we are writing. So this is equal to n into k minus h. This is same as x of k minus h. So this will transform to, means if I consider the input sequence as xn into w raised to minus nh with the phase shift, then I can also write it as wn raised to k minus h. That means it is capital X of k minus h. So this particular property is being proved. Now what is the effect of frequency shifting? The sequence nth value are multiplied by a complex number. If h is equal to 2, suppose we are considering the shift in the DFT domain by 2 samples, then there will be the nth sample values will be shifted by this amount, e raised to minus j 2 pi into 2n divided by 8. So w8 raised to 2n. DFT of modified sequence does not show complex conjugate property as the sequence is not real. This is important. So, magnitude plot of the frequency shifted sequence. This is the magnitude plot of the frequency shifted sequence. This is the original sequence DFT. Now, what we do is we shift it by two samples. That means whatever is the value at 3 will come at 1. This value comes at 1. Then the value at 4 will come at 2. Value of 5 will come at 3. Value of 6 will come at 4. Value of 7 will come at 5. Value of 8 will come at 6. And then there will be wrap around. So this 0th value will come next, and then this value at 2 will go to value at 8. This is how we have shifted in time domain. Now when we shift it in time domain, what will happen to the sequence, input sequence. The input sequence was 1, 2, 3, 4, 5, then it was 2, 3 and 1. So what will happen to this magnitude of the sequence? The magnitude is this, but it will change the phase. How the phase will change? For first sample, it will change by some amount. For the second sample, it will change by 2 times the phase. So here if the phase change is x, here it will be 2x, 3x, 4x, 5x, 6x, 7x, 8x. So increasingly the phase change occurs. The phase change is linear phase change occurs. Property of multiplication of the two DFTs and circular convolution. So as we know, time domain multiplication results in the convolution in the transform domain. Similarly, if it is multiplication in the transform domain, it will result in the convolution in time domain. So what will be the inverse Fourier transform of inverse discrete Fourier transform of x1k and x2k? It will be represented by x3k, and if we take inverse Fourier transform, this x3m will be represented as the convolved sequence. So this x3n is nothing but the convolved sequence, right? This is the convolved thing. This is multiplication in the transform domain, but it will result in the convolution. Just see, x3m is equal to, we are writing for this discrete Fourier transform, second discrete Fourier transform, and wn raised to minus mk. Here we are using the variable as n, here we are using the variable as l, because we want to write x1, capital X1k and capital X2k. Right. Now, x3m is equal to x1n can be taken out. This is x2l. It's also written as second summation. And under this summation, this is n k varying from 0 to n minus 1. What is the k term? Wn raised to minus k, m minus n minus l. But this m minus n minus l is the integer multiple of n. If it is so, then it will be equal to capital N, otherwise equal to 0. So I can write it as periodic with period equal to capital N, m minus n into p into capital N if it is integral multiple of capital N. And then in that case, L can be written as m minus n with a periodic sign. So in this case, x1n into x2 of m minus n, which is periodic with period equal to capital N, but x1n into x2 of m minus n is what? This is convolution of x1n and x2n. So multiplication in transform domain results in the convolution in the time domain. So how we do the circular shifting? Circular shifting, see, original sequence is 1, 0, 1, 2. Suppose this is so, then circularly shifted sequence by one sample will result in what? This will be shifted here, this will be shifted here, this will be shifted here, and this will be coming and shifting at the first position. So this is how it is circularly shifted. Circular convolution. So how circular convolution will be carried out? Circular time, firstly there will be time reversal, then there will be sample by sample multiplication, then we circularly shift the sequence by one sample as we have seen just now how to shift. Then there will be again sample by sample multiplication and repeat until circular shifting results in the original sequence, right? So this particular you can say number of steps is same as we understand for convolution. This we know. Only thing is in this case we will have to do the circular time shifting and then do the convolution. Circular shifting and circular time reversal will be taking place. Now let us see how it is. Now suppose xn is 1, 2, 2, 1. 1, 2, 2, 1 is the first sequence. The second sequence is 1, 2, 1, 0. I will first reverse it in the time domain, time reversal. So 1, 2, 1, 0, how it will be time reversed? 1 will be kept as it is. This 0 will come here, 2 will go there. So 0, 1, 2. This is now circularly reversed. Now what will happen? I will take multiplication 1 into 1 and 2 into 1. So this is 2 plus 1 and this also 2. So 2 plus 2 plus 1, it becomes 5. Now what I do, I circularly shift it towards right by one sample. So 1 goes here, 0 goes here, 1 goes here, and 0 comes, this 2 last sample comes at the 0th position. Now again do sample by sample multiplication. 2 into 1 plus 2 into 1. So 2 plus 2, 4, 4 and then 1. So this will become 5. Now again shift it towards right, 2 comes here, 1 comes here, 0 comes here and 1 is circularly shifted at the 0th position. Again do sample by sample multiplication, 1 into 1, 1, 2 into 2 plus 4, 4 plus 1, 5, 5 plus 2, 7. So this is 7. Similarly, if I shift it again once and if I do sample by sample multiplication, I get 7. So here is a 4-point sequence, here is a 4-point sequence. So the resulting sequence will also be a 4-point. But actual convolution is called as linear convolution. And for linear convolution, if there are 4 points here, 4 points here, how many points should be there in the linearly convolved sequence? It should have 4 plus 3 minus 1. So actually 6, right? So instead of 4 points, I should get 6 points. So here it is something going wrong. So what we'll have to do is we'll have to convert the circular convolution in the linear convolution. So how we go about doing it? What we should do it, this should be the result. It should have 6 values in the convolved sequence. So if we want to convert the circular convolution to linear convolution, what we'll have to do is we'll have to append zeros. How many zeros to append? See, in case of in order to simplify the calculations, instead of using DFT, we'll be using FFT. FFT uses the number of points as 2 raised to some power. So better use 8 number of points. So for 8 number of points, I'll have to append 4 zeros here and also 4 zeros here. So if I append these zeros, what will happen now? So I append 4 zeros to xn, I append 4 zeros to hn. And now again do the same process. Find out h of minus n. H of minus n will be what? These zeros will come first and then this will be 1 and 2. This 1 and 2 will be coming. Again do circular shifting by one sample and after circular shifting again do sample by sample multiplication. So do the process of convolution and now see what you are getting. 1, 4, 7, 7, 4, 1. You are getting 6 samples and further 2 samples are 0. So by appending extra zeros, no harm occurs and I am getting all 6 samples as expected. Thank you so much.